So for the last example, we were looking at something that is a regular item. It's just a ball that we can picture throwing. The de Broglie wavelength on that was incredibly small. It's not a particularly important concept for everyday items, but when we get to really small things, it is important. So in this particular case, you can read the question, and you'll see that we're working with an electron. So if we know we're working with an electron, we know a couple things. We know the charge is going to be 1.6 times 10 to the negative 19 coulombs. And we know the mass of the electron is going to be 9.1 times 10 to the negative 31 kilograms. So in this particular case, we're trying to figure out the de Broglie wavelength. So wavelength is equal to h over mv. Now the first thing you're going to notice in this case is we don't know the speed. Well, why is it moving? It's being accelerated. So if we're accelerating it from rest, that means it's got energy. In order to have energy, and it's moving energy, we know it's kinetic energy. Unfortunately, we don't know what that kinetic energy is, but it does come from a change in electrical energy, which is Q delta V. So we can go ahead and we can plug in our values here of 1.6 times 10 to the negative 19, and we have a voltage of 52. And when we put that into our calculators, we get a value of 8.32 times 10 to the negative 18 joules. Yet again, very, very small. But we can plug it in into this equation here. And although it's a small energy, the mass is even smaller. So when we work this out, we end up with 4.28 times 10 to the 6 meters per second. Now we've gotten information that we can start to solve for this wavelength here. So we'll go ahead and we'll do wavelength is 6.63 times 10 to the negative 34, 9.1 times 10 to the negative 31, and 4.28 times 10 to the 6. So when we plug all that information in, we get an answer of 1.7 times 10 to the negative 10 meters. Now yet again, this seems like a really small number, but remember, the diameter of a hydrogen atom with its electron floating around is equal to 1 times 10 to the negative 10. So in this particular case, this value we've got here is larger than the diameter of a hydrogen. So in this particular case, the wavelength is very significant.